The difference between an average programmer and a great programmer is data efficiency. When working with large sets of data, even the smallest of bad programming choices can lead to large runtime lags. Evaluating your program's needs is essential so you can choose which data structures to utilize, down to the simplest concepts such as what type of list to store your data in. Even the humble list is complex in its nature. In this explanation, I'll explore 3 different types of list data structures and the situations in which each should be used. Imagine that I'm going to store each piece of my data in a box. Now, I have to figure out how I'm going to arrange my boxes of data. If I know exactly how many boxes I'm going to have, I can use an array, which resembles a large box that's filled with smaller boxes of data. Each box of data is called an index. An array has a fixed size, so if I decide to add another piece of data, I couldn't add it onto the end of the array. I would have to delete one of the data points to clear a space. Additionally, if I were to delete a data point, the index would remain empty, which could cause issues in a program. While simple, the array is an excellent choice if you already know the amount of data you are going to use. The next data structure is very similar, since it's based on the same underlying structure of an array. An array list is great for when you don't know how much data you're going to have. As you add data to an array list, new indexes are created to hold them. An array list is size flexible, which is great for conserving data storage, as you only use exactly what you need. The problem, however, lies in inserting or deleting data. If I insert a data point, everything after it is pushed over it and has to be computationally moved over one index. The same goes for deletion. It's great that I can insert or delete, however, it uses a lot of computational power to do so. If I'm constantly moving every index in an array list of size 1 million, it's going to cause a lag in my program. This problem can be solved using the third data structure, the linked list. When I use an array list, my boxes of data are all nicely arranged in a line. However, in a linked list, indexes are spread out, randomly placed where memory has a blank space. Each index, which in a linked list is called a node, has a pointer which connects it to another node, called its child. That node is connected to the next node, and so on and so on. It is a little harder to access each piece of data and look at it, since you have to go through pointers, basically on a scavenger hunt through your memory. The great part is, if you want to add a piece of data in between 2 nodes, you simply create a new node and replace the existing pointers with new pointers. If I want to delete a data point, I simply change the pointer to isolate the original node, then delete it. Think about what operations your program will use before you write it, and take these factors into account when choosing your list data structure. This will help your program run more efficiently, which could be essential if you're dealing with large amounts of data.